So, welcome to Astronomy 101. This is going to be week 6, where we basically just, hey Todd, we basically are just going to do a lot of physics. This is our crash course in physics today. I'll try to go through it as painlessly as possible. It's, like I said, it's going to be recap, of your high school or middle school. Oh, hey, Haley. Hey, Becca, of your science classes that you've taken before. But this is all the stuff that we're going to go through today. Even though it is physics, it is relevant to the type of things that we're going to see in astronomy a lot. So these are the physics laws that we need to know, we need to remember, we need to refresh, whatever we need to do. Because we'll be referring to these a lot as we get into more and more complicated astronomy concepts. So, hi everyone. Thank you for joining us. All right, so let's just dive in then. So last week we learned Kepler's 3 laws. Now, the reason we do it in this order, awesome. The reason we do this in this order is because this is how kind of astronomy came into being. Started with Kepler's laws and then got into Newtonian physics. So there are cause and effect component to it. But remember, Kepler's 3 laws. 1, a planet orbits the sun in an ellipse. Remember, that was the big thing they had to get over to understand the heliocentric model. The idea that the sun is at the center of our solar system. They struggled for so long both with Earth-centered as well as sun-centered because they expected orbits to be perfect circles. So Kepler realized that if we put them in ellipses with the sun at one focus point, then that fixes everything. As they orbit the sun, they sweep out equal areas in equal time. So this is where we drew the ellipse. And then as it's moving through the ellipse, it'll sweep out. You calculate that area versus over here. It's like a shorter triangle, but it's much bigger. Basically, they're going faster, closer to the sun, and slower, further away. Again, had no sort of necessarily physics concept behind it, just observation. And then the planetary orbits follow a precise relationship between time and distance, such that the planets that are closer to the sun orbit much faster. Their years are shorter than the ones further away. Again, no physics explanation for this, just that's what we see. That's how we're able to predict things. And then Galileo's coming along and kind of getting people past the idea that the universe isn't perfect. We see things like, craters on the moon, sunspots on the sun. We're able to observe moons going around Jupiter. We're able to image, Venus phases. All of these things Galileo did that really cemented the heliocentric model of the solar system. So that was then. As they moved on, people started to get more okay because they were able to predict things. There wasn't that uncertainty in these prediction tables. Along came Newton. And Newton was from the 17th century, and smart guy, smarty pants, came up with a lot of the physics concepts that we use to describe this. Now, the field of astronomy is observing the universe around us. What is up there? Oh, thank you, Billy. What is up there, how often we see these. The astrophysics part of the field is using physics concepts to apply, to predict, to observe what we're observing up there. So why the sun looks the way it does, why planets orbit the way they do. What Kepler did was very much astronomy. What Newton contributed was very much moving into that astrophysics realm, how you apply the laws of motion, any of these things to what we see in space. That's why sort of most degrees, even if they say they're in astronomy, it's really astrophysics that is the field of study. So the first thing we're going to do is talk about what motion is. When we talk about motion, we're going to use concepts that we use a lot in our daily lives, but I want to actually break down specifically what the physics is that we're talking about. So speed. Speed is just saying how far something will go in a period of time. For example, 60 miles per hour. When we talk about velocity, we don't say velocity that often in our everyday life, but that's really just saying how fast you're going and in what direction. So saying I'm going 60 miles an hour due north would be something's velocity. And that's really important, and that's usually what physics more deals with. So physics requires both the direction and the speed to be able to do analysis, to look at forces, to look at all of that stuff. Now, acceleration is a change in velocity, and that's that key there, right? That something can be turning or slowing down, and it can be changing velocity. That's an acceleration. If it's turning, it might be able to stay the same speed, but because it's changing directions, we do say that it's experiencing acceleration. The reason that Newton kind of came up with this and was able to come up with it was because this is actually calculus. So I'm so sorry for any of you who had bad experiences with calculus, but if you're actually, the history of calculus and physics are really integrally tied because of exactly this. So it's essentially going from position to velocity to acceleration is exactly derivatives of each other, right? So if you take the derivative of acceleration, you get the velocity. If you take the derivative of velocity, you get position. So it's all over time, right? If you remember the d dt, the change, or sorry, oh my God, I did that backwards. The change in position over time is velocity. The change in velocity over time is acceleration. It's the second derivative of your position. So we don't have to we're not going to teach calculus, but I just want to mention that, okay, I'll say it one more time. But I do just want to mention this because it's an interesting tie. I think people don't realize they always took calculus and then they took physics, and there was never sort of that, oh, these are the same thing. All right, so if you have taken calculus, picture those curves. If you remember, sort of, you have a line that does that, you take the derivative, you get that, you take the derivative, you get that. If you didn't take that and that means nothing to you, then don't worry about it. So when we talk about a change in position over time, that's what we're talking about velocity, right? Change in position being 60 miles. I went from 0 to 60 in an hour is 60 miles per hour. So that's our speed or our velocity. When you say, all right, I accelerated to maybe, let's say, 120 miles per hour in an hour, let's just make it easy, then you're saying, all right, I accelerated 60 miles per hour in an hour. So that's 60 miles per hour squared. So we're going from position, where something is. You take the derivative, the time derivative, that d dt from calculus. Change in position over time is speed. And then that change in speed, velocity. For this purposes, we can use them interchangeably, but I just want to make that clear. But that change in velocity over time is now your second derivative. So you had position, speed, acceleration. Position, velocity, acceleration over time. So we're taking the time derivatives as we go. Again, I won't have to get in any more calculus than that. I just want to make that clear. And that's why Newton is credited with physics and calculus. The acceleration due to gravity, so when we drop something, objects accelerate. They gain speed as they fall. We'll go into why that is. But on Earth, that's a very specific number, and it's universal. The acceleration of a free-falling object is about 9.8 meters per second squared. It has to do with the mass of the Earth and how far away from the center of the Earth we are, the radius. The Earth is mostly round, so we can use 9.8 meters per second squared as a pretty good approximate of that. There are variances, which will mean you're slightly further away from the center and then slightly closer to the center. I went to college in Boulder, which is a mile high above sea level. So our acceleration due to gravity is very, very, very slightly less, but very, very slightly. And like I said, it doesn't matter what the mass is that you drop, because you're on Earth. It's just the mass of the Earth and how far away from the center of the Earth you are. And we'll go into the physics equations of why that is. If you do have a question on that, please hold on to that, and I may get to it by the end. But we'll revisit that, why that is the case, because that's really important. So we have speed or velocity, acceleration, and then that acceleration due to gravity. Other physics concepts that are very important here are momentum. So this is properties more of an object itself. How much mass it has, how much stuff there is, and how fast it's going is an object's momentum. You might remember momentum is mass times velocity. A force is something that you apply to an object that will change its momentum. So if you want to change the velocity, if you want to accelerate something, right? If we're accelerating it or decelerating, we're changing the velocity or changing its direction, it requires a force. This is where we get F equals ma, right? Because you have the change in velocity over time is acceleration. A force is what's required to make that change. We'll do Newton's 3 laws next. Net force is where you combine all those forces together. And that's really important when we talk about conservation laws. And particularly in astronomy, because we're in space. And so we have more isolated systems. Here on Earth, actually, classical physics, looking at this momentum, looking at friction, looking at gravity, all of that stuff is a little bit harder to do because we're on Earth with an atmosphere, with a radius, with this force of gravity. All of that kind of complicates physics. In space, the net forces are pretty straightforward. When you're away from any gravitational well, you talk about pushing something, it's just going to be whatever you're pushing. Whatever force you're applying, that's your net force. But here on Earth, we have to account for all of these other forces, like the atmospheric drag, gravity, all of those things are all forces that you have to account for. Now, angular momentum is very important to astronomy. I don't want to dwell on it too much because we can really go down a rabbit hole. I mean, when I teach angular momentum in Physics 101, we usually spend a week, just like a few classes, just trying to teach angular momentum. A lot of it's pretty intuitive. The big thing to remember is that angular momentum, this is just the momentum from a rotating or an orbiting object. A lot of it just has to do with that these same conservation laws of momentum apply. Remember, in space, objects rotate and they orbit other things. So it's really that angular momentum is the most important one when it comes to astronomy, because we don't have a lot of outside forces that are acting on planets or gas clouds or anything like that. We really just have gravity, maybe some light. But the overarching thing is this angular momentum that you get from rotating and orbiting objects. Torque, I'm just going to say, again, I'm not dwelling on it, but torque is the force, is the word for the force that we use to change an angular momentum. So if you've thought about this before, maybe if you're like trying to get something to turn, if you're trying to unscrew something, you're applying a torque to it. You're applying a twisting force that's trying to get it to rotate. If you're trying to roll something down a hill, it's a twisting force that you're trying to do. If you're trying to get something to roll and you're just shoving it, it's not going to roll. You got to apply some either above or below to try to get it to rotate. So I hope that makes sense. Now, the old mass versus weight idea, again, this is something you may have heard either in your science classes or at a science museum. Your weight is not your mass. Here on Earth, we interchange it because of that acceleration due to gravity. Mass is the amount of stuff we have, and that's whether you measure in kilograms or in pounds. And in this era of quarantine and pandemic, I think our masses are changing a slightly unexpected or unpredictable basis. But it's the amount of stuff. It's what we usually, it is what we mean when we talk about our weight. What we really mean is our mass. It's measured in pounds and kilograms. Weight is the mass and the forces acting on it, in this case, gravity. You measure your mass by standing on a scale. What that scale does is it measures your weight because your mass is being pulled down due to gravity. So it measures that force, that what gravity is acting on your mass, and the scale divides out the gravity. So you're left with the mass. That's how scales work. Because that 9.8 meters per second squared, that acceleration due to gravity, that's the force your body is feeling that's pulling you down onto the scale. They divide out 9.8 meters per second squared, and you get left with the mass, and that's what you read. That's why it doesn't matter how heavy or light you are, the acceleration due to gravity on Earth is the same. Now, some of you may have heard about this before, where we talk about, like, if you took a scale to the moon, you would weigh 1/6 of what you weigh now. And your mass wouldn't change, but because your scale is accounting for Earth's gravity and the moon has 1/6 of Earth's gravity, it will divide out Earth when really it should just divide out 1/6 of Earth's, and then you would still get the same mass. So, sorry. Another interesting example, if we were in, yeah, exactly, Valencia. Because it's hard. And another example that if we were in a classroom, we would absolutely go and do and spend some time playing around with is taking a scale into the elevator. Because the elevator experiences acceleration and deceleration in a vertical way. And so you're experiencing the acceleration, the change in speed in the elevator, plus the acceleration due to gravity on Earth. So if you take a scale into an elevator and hit up, what's going to happen is that your weight is going to look like it goes up. Your mass is going to increase because now you've got this acceleration that's kind of pulling you down, plus the acceleration due to gravity is going to pull you down. When it decelerates, you're going to lose some weight because now the acceleration is counteracting, and it's going to sort of remove some of the effects of Earth's gravity. So you can do that. If you wander around a physics department often in the normal times, you would usually see a Physics 101 class carrying scales into the elevators to go do this. But we do know this intuitively, right? You can feel that when a elevator moves, your weight is changing because that is the forces acting on your mass, but your mass is not changing. The amount of pounds or kilograms you have does not change. Now, free fall and weightlessness. The ISS, the International Space Station, we see the astronauts in the International Space Station appear weightless, that they have no forces acting on them. Now, obviously they don't have zero mass, they have zero weight. They're experiencing weightlessness. The International Space Station is actually in low Earth orbit, so it's still actually close enough to the surface of the Earth that it's affected by Earth's gravity. It's not that these astronauts are weightless because they're in space. They're weightless because the International Space Station is falling around the Earth, which is slightly horrifying. But if you've been on one of those free fall rides at a theme park, the way that those work is they drop you and they accelerate you at the acceleration of gravity. So it's falling as fast as you are, and you are then experiencing weightlessness. What the International Space Station is doing is, if you imagine you have a baseball and you throw that baseball, it's going to go a certain distance and then it's going to fall. And then you throw it harder, it's going to go a little bit further and then it's going to fall. And if you keep consecutively beyond our own physical capabilities, but imagine you keep throwing that baseball so far and so hard, it's going to start to fall, but the Earth is round. The Earth will curve away from it. And so as it starts to fall, it has no ground to land on, and it's going at a speed that it's never going to land on a ground. That's what the International Space Station is doing. It is up in space, and it is just launched at a speed that as it's falling, the ground keeps missing the ground. And that's one of the reasons that they say that the astronauts you have this nausea, that when you get up there, you feel nauseous, and it's because you are falling. but it's constant, and so it is something that your body is able to get used to, but it does take adjusting because it's just a constant free fall around the Earth. And that's why they look weightless, because if you take a scale, it's like you're trying to take a scale on an elevator that's in the free fall. You're never going to be able to stand on it. That's the case in the International Space Station. Slightly horrifying. When people ask me if I want to be an astronaut, I tell them that, and then they're like, oh, okay, I get it. But being an astronaut is objectively cool. This is Peggy Whitson. She's the one who's sort of serving lunch right there. She's set the record for hours in space. That woman lives in space. She's awesome, and we love her. And if you've never heard of her, look up Peggy Whitson, and you will love her too. All right. I've kind of danced around these a little bit, but really the big things that are important at this stage is this idea of velocity, acceleration. So velocity is a speed plus a direction. Acceleration is a change in velocity. This idea of momentum, angular momentum, and forces is important. Those all kind of dance around Newton's laws of motion. So Newton had 3 laws of motion. The first one is an object will move at a constant velocity if there is no net force acting on it. So there are key words here that we've already gone through: velocity, speed plus direction, and net force, the combination of all the forces acting on it. If you have one force pushing you this way, but an opposite force pushing you this way, you are feeling 0 net force, so your velocity won't change. And essentially what this is, an object at rest stays at rest, and an object at motion stays in motion. That's really what Newton's first law is. If you just set an object down, it's at rest. It's not going to move unless you push it. Now, we kind of know that. And then an object at motion stays in motion. This is a little harder for us to grasp because we're used to Earth. The physics on Earth, there's air drag, there's friction, there's all these things that slow it down. All of those count as forces that slow down objects at motion. But if you hawk something in space, it will just keep going at that same velocity. A great example of this, and I didn't write it down, so I can't remember the Futurama episode where they launch Bender's taking a nap in the torpedo tube and gets launched out into space and keeps going at the same speed, tries to slow himself down by throwing stuff away from him, is brilliant. That's a perfect example of Newton's first law of motion. But I want this course to live on the internet. I don't want it to get taken down for licensing reasons, so I'm just going to say the episode, not actually show a clip from it. Now, the second law of motion, this is what happens to an object when a net force is present. Now, if you've taken physics before, you may remember when you had the exam on Newton's laws of motion, you wrote down object in motion stays in motion, rest stays at rest, or constant velocity. And then the second law of motion, F equals ma. That's usually what people... Just remember, the second law of motion is F equals ma. But really what it is what I was describing earlier, that force is what's required to change something's momentum. Momentum is the property of an object, its mass times its velocity. If you're not going to change its mass, right, we think most objects, if we set it down, it's got its mass, I'm not going to add to it. If I want it to move, then I'm just going to be changing its speed. That's going to cause it to accelerate, to go from 0 to some speed. There's an acceleration due to a force, me pushing it. So it's really the force is the change in momentum. Or F equals ma. And then for any force, there is an equal and opposite force. This is one that sort of most people remember when they're trying to take their test on Newton's laws of motion. Rocket ships, rocket ships, rocket ships. How you launch rockets into space is you spit a bunch of stuff out of the bottom. The rocket goes in the opposite direction. For every force, there's an equal and opposite force. If I'm pushing on an object, I am pushing this direction. That object is pushing back on me. It's a little bit... just think of the rocket ships. People have different analogies for what works for them and what doesn't. It's really just, you got to think equal and opposite forces. Anytime there's a force in one direction, it's pushing back on the other. This one we see the most, when you're talking, Valencia mentioned like sort of doing experiments in space. If you're trying to do repairs or anything like that in space, you push something down this way, you're going to go in the opposite direction. There's just this equal and opposite thing that happens. If any of you have watched Space Force, it's a really good example of this with the monkey and the wrench. That's all I'll say. But equal and opposite forces are important to remember. Very funny, very accurate. I worked with about a dozen John Malkoviches from Space Force. It was a little close to home. That dude definitely just sat in our offices and observed behavior. So anyway, but yeah, equal and opposite forces. All right, so conservation laws, these are important to physics wholesale, but how they necessarily apply in astronomy, like I said, the first one is conservation of momentum, and it'll primarily be angular momentum when we're talking about this. But conservation of momentum in a physics-wise, best examples from this you may remember from like a Bill Nye episode or something, where you have a truck filled with marbles, it crashes into a wall, all the marbles bounce out of that truck plus the marbles, that was its mass, and then when it crashed into the wall, its velocity stopped, but then all those marbles have their own momentum. The momentum before and the momentum after is equal. Another good one, again, if you live in a university town with a good pool hall, you will most likely see a Physics 101 class doing a lab experiment at a pool hall, because conservation of momentum applies a lot to pool or billiards, where you shoot an object, you have a ball with a mass at a velocity, it hits a bunch of other masses that have zero velocity. That ball stops, the rest of them start moving, but they don't move as fast as that original one did, because you have momentum before and after the collision, and it's equal. The momentum is conserved. So, yeah, I think we're good with that. Like I said, this is one of those things that's actually a little bit easier in astronomy because we have these isolated systems. You have collisions in space. You're not having to worry about friction or air or anything like that. So the conservation of angular momentum, like I said, this is really what we see a lot of. The orbital angular momentum. So angular momentum is measured by mass times velocity times how far away you are from something. So if you are swinging a ball around on a rope, the orbital angular momentum of that ball will be its mass, its velocity, how fast it's moving, times the radius, how far away it is from you. This is the solution to Kepler's second law, that, over an equal period of time, planets will sweep out equal areas. It's because of this. And it's because we talked about when a planet is closer to the sun, the R gets smaller, it moves faster. The velocity increases. So this goes down, that goes up, and this number stays the same, and its mass hasn't changed. So if it's further away, this number gets bigger. It slows down, this number gets smaller. That work? I think that works. Because the whole thing is that this is conserved. This stays the same. So if something changes, something else has to change in the opposite way to keep that equal. So Kepler's second law, when they're close, that's down, they're going fast. When they are far away, that's down, that goes up. When they're far away, that increases. The radius gets bigger. This is why I have to say it out loud. The radius gets bigger, they're further away, they slow down. The velocity gets smaller. Overall, the angular momentum is conserved. Okay. Rotational angular momentum. This has to do when... this is more talking about a single object that's rotating. And it still applies. The calculation still works. It's just sometimes a little bit harder for us to wrap our head around. This is the spinning... Oh, Discord link is down below. No worries. Discord link should be in the About section somewhere, at least in the big description. You might have to change tabs. They changed the layout of the streaming page, but... Thank you. Sorry, I don't have it handy right now. I have all my all my stuff up. I'll throw it in at the end of this, though, if you're still here. So, but thank you for lurking, and no worries. But the rotational angular momentum, that's that thing with like the, ice skater that's spinning around, the arms move closer together, and then and then that ice skater spins faster. This will come into play as to like why you start with a big nebula, and then as it rotates, it starts to flatten out. We will talk about that in the future, but that is rotational angular momentum. And then conservation of energy in astronomy is incredibly important too. All this says is that any action involves an exchange or a conservation of energy from one form to another. So it doesn't necessarily have to change in the same form, but it can be transferred regardless. So kinetic motion, kinetic energy is the energy of motion, of movement. This includes thermal energy. So thermal energy really just means the motion of tiny, tiny particles. When an object is hot, the particles, the atoms that make it up, are moving very, very fast. When an object cools down, its atoms are moving slower. And so thermal energy is kind of a subset of kinetic energy. Radiative energy, this is just light. So when we talk about a sun giving off light, it's giving off radiative energy. That can be absorbed. We've talked before about like solar sails, you get hit with light energy and then it gets transferred. Yeah, valid. You had to buckle down and do all the homework. Yeah, I'm not going to dwell on, this is, like I said, we're just doing a quick overview of Physics 101. This is not something anyone needs to get hung up about. I just want to lay these concepts out there so we have them as we go forward. And then potential energy. Most people think of potential energy, that's, something's gravitational potential. If it's hovering high or it's about to fall in, it's got gravitational potential energy. If you let go of it, it will start moving, it will fall due to the force of gravity. And mass energy is also potential energy. If you followed me for a while, you may be familiar with this idea of how we've talked about like warp drive and all of that. You use E equals mc squared, that energy equals mass times the speed of light squared. What that really means is that there's energy stored in the bonds of matter. And if you release that energy, then that potential energy is then transferred to kinetic, radiative, thermal, all of that. But there's energy stored in molecular and atomic bonds. And that's what we call mass energy. All right, last thing-ish, mostly the last thing. The universal law of gravitation. This is kind of another big thing that Newton contributed to. What they realized as he's putting together these laws of motion that, when we drop something, we talk about mass versus weight, we talk about collisions, we talk about the net forces that objects feel. A big contributor is kind of invisible, right? It's just because we're here on Earth. And that's this universal law of gravitation. As he broke it down, he said basically every single mass that you have attracts every other mass through a force called gravity. That there is this force between two massive objects that will be attracted to each other, and we call that gravity. It's analogous to like magnetic forces that, you have a positive pole and a negative pole. They're attracted to each other. Gravity just says that their intrinsic mass, they feel this force that we call gravity. We are not going to get into general relativity, Einstein, any of that. We are in Newtonian physics right now. Stuff that applies to 99%. We will treat gravity as a force between two massive objects. The strength of that force is directly proportional to the combination, the product of those masses. So basically what that means is you take both masses and you double one of them, then that gravitational force that they're feeling is going to double as well. If you multiply both by 2, then the combination of that, they're going to go up by 4. So it's directly proportional. You change the mass, the force of gravity is going to change. the strength goes down by the square of the distance, how far away apart these two objects are. If they're this far apart, they're feeling a force of gravity. If you double that distance, then it's going to go down by a factor of 4. Double 2, square that, so it's down by 4. This is in equation form. I try to limit the amount of equations we do in this class because it's just not fair. But this is really Newton's law of gravitation, right? We have those two masses, mass 1 and mass 2. So that's where the directly proportional comes in. So if this one, you put a 2 in front of it, that's going to make this force go up. You double that one, that's going to make that go up. And you put a 2 in front of each of them, it'll go up by 4, just like I said. And then here we have r is the distance between them. That's all squares. So if you put a 2 in front of the r, then that's going to all be squared and it'll go down by 4. And they both feel the same force. Now this g is one of those universal constants. It's just a number that you use. 6.67 times 10 to the negative 11th. I don't remember the units, but that number is drilled into my brain. But yeah, so it is an equation, but it basically just summarizes what we said here, that they feel this same force that we call gravity. That gravitational force is proportional to the masses, and then it goes down as the square of those masses. Now, I am going to pause here and do an aside. I don't want to spend too long on this because, we're running out of time a little bit. But a lot of people will ask, okay, well then why doesn't it matter if I stand on a scale versus my friend who stands on a scale? Why is it all still the same acceleration due to gravity? Well, because remember, we're talking about the acceleration due to gravity, that force you feel due to the acceleration, due to, if you let something go, it's going to fall and it's going to accelerate. So we can set this equal to ma, mass, my mass, times the acceleration due to gravity. That mass, my mass, will cancel out of both sides, left behind with the mass of Earth. So that's why it doesn't matter whether it's a hammer, whether it's me, whether it's a bowling ball, whether it's a bulldozer. It's always going to be 9.8 meters per second squared because we have that ma on this side. That F equals ma is equal to this, and that m cancels out. If I lost you, don't worry about it. Don't get hung up on it. We can revisit it later if you want. All right, so gravitational slingshots. I just want to pull in some quick examples of where we see these affected in astronomy. I've talked about gravitational slingshots before. This is an awesome poster you can buy if you search for the chart of cosmic exploration from Pop Sugar, I think. You can buy it on there. But what this is doing is it's showing the motion, the path that every single spacecraft we've sent out into the solar system has taken. But the reason we do gravitational slingshots, what that really is using the force of gravity as a way of transferring momentum. So it's almost like a collision. You get close enough that you've collided with the object, but what you're doing is you're transferring some momentum from your spacecraft to the other, whether it's gaining speed or it's slowing speed. Because your spacecraft is very, very tiny and your planet is very, very big, combined it's the same momentum, right? And you transfer momentum, so your spacecraft is going to gain a little bit of speed. Masses aren't changing. The planet is going to lose some speed, but overall, it's going to, because its mass is so much bigger than the spacecraft, that speed that it's losing is like negligible. It's hardly anything. That's why it's so great. The reason that we can do gravitational slingshots is because that mass ratio between the spacecraft to the planet or the sun is so different that the spacecraft is going to speed up a lot, and the planet is hardly going to feel it at all. Very, very similar to if you were to flick a marble at a bowling ball, that marble is going to shoot off in another direction. That bowling ball is going to barely move. It's just that mass ratio. You've still transferred momentum, but it's hardly anything to that bowling ball. But yeah, so it's all a transfer of momentum. We do this in astronomy all the time. Tides. So talking about the force of gravity, really quick, we're going to talk about tides. So we do get tides caused by the moon. people may have heard this before. I hope we're able to understand it a little bit now. Because of Earth's rotation, the tidal bulge is like slightly offset from where the moon is. It like sits slightly at an off axis from it. But it's basically getting pulled in this direction, and then Earth is rotating in this direction. Because the ocean is around us, it's a fluid, so it does actually bulge a little bit. And then we do get this equal and opposite reaction. The analogy that I've always struggled coming up with a good analogy for why it bulges on both sides. The best one that I read is basically like if you take a rubber band and you have one side stuck and you pull the other side, the side that's stuck is still stretching. That doesn't quite work for me. The other thing is just saying it's equal and opposite. Feel it on one side, it's going to be felt on the other side. Or you can just say it affects both sides. But it's the gravity due to the moon. But the moon is smaller and close, but the sun also has a pretty big influence on our gravity. And as such, it has an influence on the tides as well. Now remember, I hope we've been learning as we've been going, but remember the moon orbits the Earth every 29 and a half days, so the tides are going to kind of change on a scale depending on where the moon is, particularly relative to the sun. So if you've heard of spring tides and neap tides, this is where if the moon and the sun are in the same line, then you get a spring tide, where the bulge is going to be a little bit more extreme because they're combining their forces. If you're getting neap tides, you're still going to be feeling a slight bulge, but it's going to be way, way less. The reason that even though the sun does have a gravitational effect on the planet and the ocean, and as such the oceans, it's because the distance ratios, the fact that the sun is really far away, the Earth's radius is really tiny compared to how far away it is. So whether it's here or here, on one side of the planet or the other, or here or here, you're not going to be getting a big bulge. You're not going to be getting a big extreme. You're basically going to be feeling the same amount on each side, as opposed to the moon where it's closer. It's smaller, but it's closer, so you feel it favor one direction. But when you do have the sun, it does still have an effect, and the presence of the moon will counteract that. So here they do compound, here they do pretty much counteract, just because big, far away, small, close. All right. So, to recap, lots of Physics 101. Please don't get too hung up on it. This is not a physics class. Bear in mind, I am choosing to teach Astronomy 101. I am not choosing to teach Physics 101. I love it. It's important. It's what my degree is in, but it's not as cool as space, in my opinion. All right, so describing motion. We talked about speed, velocity, acceleration. We talked about momentum and angular momentum. Momentum and angular momentum being... there is no exam and there's always an open book. Momentum being the combination of mass and speed and velocity, and angular momentum being the speed and the either orbit or rotation. We talked about the different types of forces. You know, we have kinetic, that thermal. We talked about potential forces. We talked about the gravitational forces. Newton's laws of motion. You have the object at motion will stay at motion, where rest will stay at rest. F equals ma, and equal and opposite forces. It's drilled in. Conservation laws. Conservation of momentum basically says that you can transfer momentum, whether it's through mass or through velocity, but it's going to be conserved over the same system. Just think of playing pool. And conservation of energy as well is really really important. If it didn't quite sink in, because this was just a fire hose of information, don't worry. We will be coming back to it and revisiting it a lot. But it's particularly thinking about like how you have radiative energy, like light from the sun will heat up gases. So, which is kinetic energy. So you have radiative energy will then heat up. And like I said, that's coming down the line. This is just laying down the groundwork. And then that law of gravitation. Two objects feel a gravitational force between them. It is directly proportional to their masses and inverse square relation to how far away they are. And that applies to planets orbiting suns. And yeah. So with that, I think that's it for this week 6 crash course in astronomy. I am going to stay on the live chat for another 15 minutes. We have some hanging questions from the week that I want to get to, but if you are watching this recorded after the fact on YouTube, please feel free to leave a question in the comments or contact me on any of the links down below. Please like and subscribe so I can keep doing all this fun stuff. And yeah, for those of you on YouTube in the future, thank you for listening. All right.